Hi, my name's Sam. I'm just going to talk you through the first poster presentation of my project, and it's about the self-cleansing peroxide mechanism to improve resilience and energy efficiency in microbial electrolysis cells. So first of all, microbial electrolysis cells use a electrogenic biofilm. So here's a schematic of one. So basically, they use an electrogenic biofilm to consume the organics in wastewater in an anode compartment. And these bacteria consume the organics into electrons, which go around an external circuit with an additional voltage to produce hydrogen gas at a cathode. So they're a promising biotechnology, and they are potentially a tool in wastewater to recover hydrogen, which is important as the UK water sector aims to achieve net zero carbon emissions before 2030. However, none of the pilot scale reactors that have operated previously have produced high levels of hydrogen production when operated on real wastewater. And this typical hydrogen production rates have been less than 1 litre per day. And this is due to a major hydrogen sink, which was found to be through hydrogen scavenging microbes at the catholyte. So this section of the project actually aims to develop sterilization techniques to get rid of the hydrogen scavenging bacteria based on in situ electrochemical peroxide production at the cathode, and that's done by changing the input voltage into the cell. So here's the concept. So first of all, we start with a stable system where there's no scavengers present in the catholyte, and then basically we start with the biofilm growing, and as the biofilm grows, more hydrogen production takes place until it stabilizes. And then over time, you get contamination of the catholyte, and this causes the hydrogen peroxide to drop, along with the cathodic Coulombic efficiency, which represents the amount of current that is actually converted into hydrogen gas. So that drops. And then the intended mechanism is to pump air into the catholyte, and this will and also change the voltage to 0.5 volts, and this enables a 2 electron reduction reaction with oxygen to produce peroxide, and this causes the scavengers to die. And this allows the hydrogen production rate to bounce up and hopefully return to the same state as it was before the contamination event and provide some resilience against the contamination. And this will act as a basic maintenance regime of the microbial electrolysis cell, and it will allow us to assess how big the hydrogen loss is from contamination events. No other study has done this before. So the proposed methodology is to first create a calibration curve for peroxide. The second step would be optimize the catholyte over neutral to alkaline pH ranges by measuring the pH of different electrolytes for different pHs over time, and see how they degrade for each catholyte. And then the third step would be to inoculate 3 groups of reactors to determine the peroxide concentration required for sterilization. So this will be done with stock peroxide, not the electrochemical produced peroxide. And this would allow us to identify like an optimum sterilization efficiency of the catholyte with flow cytometry. And then I will investigate the electrochemistry of peroxide production on a stainless steel mesh cathode, and this will enable me to identify the optimum material to use for the peroxide production. and assess if stainless steel mesh is appropriate. And if not, this will provide direction in terms of swapping out the stainless steel mesh cathode for a carbon-based one, which is tends to have a preferential oxygen reaction for peroxide. And then lastly, I would inoculate 6 MECs in hydrogen production mode with induced contamination. Group 1 would be a control, so this would have no peroxide, and this would stay a stable voltage. And then the other 2 groups would have in situ peroxide production, and this would be compared to the control group in terms of energy efficiency and hydrogen recovery. And if the mechanism provides resilience, I'll test it in a pilot trial under real world conditions at Howden Sewage Treatment Plant. The likely outputs would be a full study that assesses the practicality of using a sterilization mechanism by generating peroxide in situ with the cathode. And it will also provide greater insight into other hydrogen sinks. So if the sterilization technique doesn't resolve the hydrogen loss issues, and we're still losing a lot of hydrogen based on the cathodic Coulombic efficiency, so a lot of conversions of electrons into hydrogen, that means that there's other routes of loss that we need to look at. So this could be through diffusion of the hydrogen back through into the anode and into the atmosphere. And it will ultimately, this study should provide some direction into addressing these losses. Thank you for listening.